And the stream is starting. Welcome, welcome. So can you all see my my screen here, the website we're looking at? All right. I've added some stuff to it. So I spent yesterday getting your first homework ready. That is available inside the homework portal. And I also spent the rest of the afternoon making a couple more videos to show you how to do it. So all of the videos that I had planned to post are now complete up here inside this first table. So there is a general video that describes how to begin to access the virtual desktop. Those steps are not program specific. They're just general to get into the virtual desktop at all. And then for each program, SAS and Stata separately, there are 3 different videos to guide you through just getting used to interacting with the system, what the commands mean, how to generate results, and then how to use the example 1 files to get started on homework 1. So the way that this will work um, in the future is that each unit that we have, so a unit to me is a combination of a lecture, example, and a corresponding homework that have the same number. They all go together. So in doing homework 1, you'll be referring to the example 1 files. Doing homework 2 refers to the example 2 files and so forth. You won't be asked to do anything that I haven't given you an explicit example for. So I'm not expecting you to generate SAS or Stata code out of thin air. That's not fair. I'm not going to do that to you, especially not in a pandemic, right? We all get extra credit just for waking up each day and trying to get through everything. That's what I think. All right. So I don't know if you had a chance to check out any of the videos, but are there any problems or questions that you've run into thus far? Ish. Pamela, you look like you want to say something.
Uh, I had a quick question.
Okay, go for it.
I just want to make sure that when we're saving things, we're really just saving the DO file, not we don't need to save anything in the stata like results screen,
That
correct?
is that
Okay.
is correct. You
Okay.
can. If you want to save the results that are in that screen, that's what the log file does. I
Okay.
tried to demo how to create one of those and ran into a problem with the file path to get to it, but there's also an option inside Status to start a log. And if
Okay.
all of that fails, there's the old school copy the stuff in the window and go paste it into a Word
Cool.
document, right? That works too. But
Okay.
you don't
Thanks.
technically need to save any of that because if you ever wanted it back, all you have to do is open up it's called a do file, the extension .do, and just run it again and it all reappears. So each of the program syntax files that you'll be typing your codes into, the one that's in SAS has a .sas extension, the one that's in Stata is a .do. Both of those are just plain text files. That means that you can open them and edit them and work with them from outside, just using any sort of plain text editor like WordPad or Notepad or something like that. The only catch is that if you copy those codes over into Word or another program that's like it that has rich text formatting, it may autocorrect your quotes into the kind that go like this, like the slanty quotes as opposed to the straight up and down quotes. And SAS and Stata do not know what to do with slanty quotes. So when you copy it back in, it will be very confused when it encounters a quote. So that's the one hitch if you are copying your codes back and forth across these things. That's why I would encourage you to use just a plain text editor for these things rather than Word if you wanted to work with your syntax. So, all right. Other questions? Pamela, did you have something?
Oh yeah, my issue. I was able to get the VPN and virtual desktop. I actually did that last week, but I have a Mac, and so I'm just having trouble trying to figure out once I've downloaded stuff where it's at. But I'm getting a new computer this weekend anyway because I need to upgrade. So I'm just going to kind of wait till I get that and then bother the IT people and have them help me
Okay.
work through when I download it, where did it go so I can actually do something with it.
Yes, you have to know where you've downloaded it to be able to tell the programs where that is. However, it becomes easier once you're inside the virtual desktop if you open up the Windows Explorer program inside the virtual desktop. So on Mac, I think there's a Finder option where you can navigate to
Mhm.
files, and there's Windows Explorer on Windows, but within the virtual desktop. If you use their application and just navigate to where it is, you can copy the address of that place and then insert it into your files. And it will be a lot easier than trying to figure out where it thinks your stuff is.
Okay.
Not where it is, but where it thinks your stuff is. Macs in particular, I've helped other people troubleshoot. You can absolutely do this using a Mac. That's not a problem. The issue is trying to communicate between the different operating systems where stuff is. So, for instance, I had a couple students last semester that already had an H drive as part of their local disk system. And so
Mhm.
they ran into problems in mapping the university's H drive because you can't use the same letter, and so their path looked a little bit different. There's folks who got used to dropping everything on the desktop, and that's like their system. And so if you look at their desktop, there's 8,000 files there. Well, that's fine until you realize that each user on your machine has their own desktop. So there's not just one folder called desktop, like there's infinitely many. So those things make it challenging to figure out where your stuff is or went when you download it. Usually, when you download something, there should be an option somewhere that points you to what location you want to save it to. And so if you
And
can find where that is, yeah,
that's what I need to find because I
yeah.
kept looking. I mean, it showed that it downloaded. I was able to find it, but then I can't do anything with where it was. So
There may
I'll,
be a default setting, like on your browser. You may have to dig through the settings on that to find out when you download something where it wants to put stuff by default, because that may be some downloaded folder that's buried that you don't normally access.
okay.
So, yeah, I'm happy to help troubleshoot. Thank you guys for taking the initiative to get started on this early. As I said before, this is honestly the hardest part of this class. It shouldn't be, but it worked out to be that more people had problems just connecting to this system and using the files than actually learning statistics. So, I'm hopefully going to learn from mistakes made in the past and try and facilitate this process for you. So, that's the goal. All right, other questions?
Yeah, I have a question, please. Just as, yeah, I think it's just a matter of navigating also. I have a Mac too, but when I was watching your video and, once you get into the application and you say like if you click on Stata or SAS, then it should open up in a new window.
Mhm.
Mine doesn't do that. For some reason, it downloads it and then I have to click on the download and then it opens up the application. Is there a way that I can make it open up automatically?
Um, I think that there is an option when you first use it as to whether or not you interact with the program through the Windows or whether you download a program that is the Citrix receiver. And if you do the latter, then I think that eliminates the step where you have to download a path to the application. So when I run virtual desktop, in the background, there's a little icon that says that it's running this Citrix thingy, this program, and that allows me to connect to it without that intermediate step.
Okay, so how do I change that then? Or do
Um,
I have to reinstall it? And then is that in the beginning when you actually set it up? Or,
I made the mistake of not showing that part in the videos because I had already set it up a long time ago. And so like mine just pops up like ta-da, it works. But I think
oh,
when when you try it for the first time, there should be an option whether you want to use the application or whether you want to just work on it through the windows. Has anyone else encountered this yet that can help
Yes.
me? Okay, Pamela, what did you do to get it to work?
I had to download Citrix first. So
Okay.
that's now on my dock at the bottom. Citrix is.
Yeah, Citrix is a program that is running the virtual desktop. And I think if that program is running on your computer, that it simplifies some of these connection issues.
oh, but I downloaded it, like I installed it. I actually had it on it before, so I uninstalled it and I reinstalled it with used through the IO program. But it's still, I'm still having that issue. So I was just wondering, but it does ask you like, does your school require like a certain ID or email connected to it? And then I just kind of ignored it. But is that the issue maybe?
Maybe? I'm not certain. I'd have to try and dig into that for you. I know that
Okay.
it did do what you're describing at one point for me, and then it stopped
Mhm.
doing it, and I'm not sure what happened in between to make that the case.
Okay.
But even if you have to download something and then click on it for it to open, it should still work from that point forward, right?
Yeah. It's
Okay.
yeah.
Yeah, so
Okay.
it's still a little bit of an extra hassle, but it should still function.
Okay. Thank you.
Sure. I will see if I can do some digging and get a better answer for that.
It's okay.
No, that's what I'm here for. Okay. Other questions? Okay, so just I'm looking at the list. The list is stationary, and you guys appear to all be stationary now, even though you're all taking turns talking. So whatever algorithm is reordering you is quiet at the time being. Yeah, exactly. Who knows? All right, so whenever you get a chance to practice with that, the material is ready. Homework 1 is not due for quite a while, but in looking at the content of it, you should be able to do everything through the end of section 1. So there's 2 sections on it, and we've covered enough to get through the end of section 1. So there's plenty to work on if you have some spare time and you'd like to get ahead. Otherwise, it's not due until the 5th week of classes on the September 21st on a Monday night. So. All right. Any other logistics software questions while we're on the topic? Okay. Then should we dive back into lecture 1? Why not, right? That's sort of a rhetorical question because, like, well, we're here. What else are we going to do? Let me get you a nice beach picture to look at. How's that? Nice little hammock there. And you can keep that in your view while I ask you, what do you remember from last time? Let me get the chat window open. Uh-oh, looks like I've missed some chats already. My apologies. Divided attention is a bear here. Okay. Proc univariate means, yes, variance is how spread out all the data is. Can we all do the hand signal that goes with variance simultaneously? There we go. Yes. That's my hand signal anyway. So central tendency, measures of central tendency we talked about, and measures of spread or dispersion. So we have central tendency, mean, median, mode. And we have dispersion, standard deviation, variance, and interquartile range is the other one. And then skewing or skewness. What's skewness? I'll take hand gestures for that too if you want. Yeah. Shh. Yeah, very nice. So there are 2 kinds of skewness, right? Positive or negative. And I can't do the hand gestures because I'm always doing it backwards. Which kind is positive skewness? Yeah, yeah, all the data is on the left side and there's sort of a tail going to the right. That's this way to you guys. There we go. Yeah. That's common in measures where you can't go below a certain point, but you can go up to positive infinity. So costs, for example, counts, things like that. Negative skewness would be when you have something called a ceiling effect, right? Where everybody has the highest possible score. There's a bunch of people sort of all at the top, sorry, this way to you guys, and then there's some distribution that curves off of that. So in terms of relating skewness and measures of central tendency, under what situation would mean, median, and mode not point you to the same number? Waiting for it? When it's skewed? Yeah. So mean, median, and mode are going to be right on top of each other if the distribution is symmetric. If most of the people are in the middle and then there's some tails on both sides. To the extent that the distribution is asymmetric, then those 3 measures are going to potentially disagree and it would matter which one you report. There's nothing wrong in reporting more than one. Let me get to the chat here, make sure I haven't missed anything. Yes, notation. Let's do a notation quiz. What is the symbol for a sample mean? Yeah, yeah, not N. Why? Yeah, why? a variable with a bar over the top. So I'm using y up to this point because that's going to be my notation for outcomes, which is the context in which we'd be reporting these statistics. But yeah, the bar over the top. What would we call the population version of the mean? What symbol goes with that? Yeah, mu. It's a Greek letter. It looks like U with an extra line on the front of it. So it's the U looking thing. But it's not a U, it's a mu. Yes. Very good. Look, making sure I didn't miss anything from earlier here. Pause me for scrolling. Do we need a mean for nominal variables or a median? Does that help our cause if we have a mean or a median for a nominal variable? What do you think? Nope. Nominal means unordered, right? Where there may be numbers, like 1 means this, 2 means this, 3 means this, but they're not really numbers. Now, will SAS, Stata, R, SPSS, Excel, or any other program let you calculate a mean for a nominal variable? Will it let you? Yes, it will. Even if it makes no sense, it will let you. So that's up to us to remember what makes sense and what doesn't. And so standard deviation, what's that? Square root of the variance? Yes, although then that begs the question, okay, what's variance? How much a data point is away from the mean on average? Yes, the average distance of any observation within a sample from the mean. That's your standard deviation. Average offness, so to speak. And if I take my standard deviation and square it, that's variance. So you'll get used to seeing one or the other reported. S is for sample standard deviation. S squared is for sample variance. For the population version, we just saw it on the window here, sigma, the Greek letter. Looks like a little circle with the line across the top of it. What is the point of squaring those deviations to make variance? We talked about that very briefly. Can't add them. They sum to 0, exactly. So the way that we get the standard deviation is actually somewhat convoluted because we have to go through variance first. So let me pull up the slide that talks about that. One moment here. This one, that's what I wanted. So we calculate variance to get to standard deviation, and variance is how far off each person's variable value, so that's the y sub I, minus the mean, then squared, then summed, and divided by n minus 1. So we square it to keep the positives and negatives from canceling out. But then the squared term is in a weird metric that's hard to interpret, and so to put it back onto the metric of the original variable, we unsquare it, take the square root, as we all discussed. You approved root, right? As opposed to root. We're still sticking with that today? Okay, square root it is, and that's our standard deviation. So that gives you a sense of how applicable, how descriptive the mean is for any one person. The higher the variance, the more spread out the data, the less good of a guess the mean is for anyone's unknown value. So variance matters just as much as the mean. All right, good. You guys remember a lot. Other things, capital N is for sample size. That's another symbol that we did. Are there any other notation things I'm forgetting? That's all I can think of too, so good. All right, so we had pictures. So in terms of getting summary information, this is things that you'll get a chance to practice doing in homework 1. To be able to get a table that looks like this. So for categorical variables, for questions that say, what is the count of people in this category? What is the proportion of people in this category? That's procfreak in SAS or tabulate in Stata. And you'll need to change the name of the data set that you're working with in SAS as well as the name of the variable, whereas in Stata you only need to change the name of the variable. To get descriptive information for quantitative variables, the central tendency, dispersion, skewness, percentiles, all that good stuff. Proc means will give you some of it in SAS, summarize in Stata, and univariate, proc univariate, here it is, in SAS will give you the rest. So 75th percentile, 50th percentile, 25th percentile, interquartile range, all that extra stuff that one might want to report as well. Okay. And then we started talking about, we did skewness, but skewness doesn't matter. In binary variables, mean and variance are tied together. So once you know the mean, you know the variance. So those are going to work a little bit different because of that. And we started talking about inference and pictures, right? Does this look familiar? Yeah, this is our new friend, the normal distribution. So we're going to use this a lot. There are other distributions that you can describe individual variables with. It is not the case that all variables need to be normal for us to do statistics on them. That's sort of a common misconception because normal is so overemphasized in early classes. But what we are going to use this thing for, or its cousin, the distribution T, is to try and make inferences from one particular sample's value up to what it would be if we knew what the population was. So it's fine to say I collected some data and the mean for this sample is 30 and the standard deviation is 5. That's fine to say. That's a descriptive statistic. But if you want to then say, to what extent does that mean of 30, is that a good approximation for what the population's mean would be? Or how far off is that 30 likely to be on average if I were to redo the study? How, what's the word I used last time? How movable is that? That would be the question. Then we want to talk about one more thing, which is going to be a combination of mean, standard deviation, and sample size, which is going to be our new best friend, standard error. So a new piece of vocabulary today that's going to go along with this. All right, so I think this is about where we picked up or left off, ready to pick up. Questions on any of this so far? No. Okay, I just lost my chat window. Okay, there it is. Didn't miss anything. If I get going and you guys type a question and I miss it, can someone please like flag me down? That way I don't miss it. And you guys feel free to interrupt at any time because it's not an interruption. We're trying to have a conversation. I'm just like that friend that just doesn't like understand when it's not her turn to talk anymore and you have to like do one of these. I'm that one. So all friendships have that dynamic, right? The person who doesn't understand when it's not their turn to talk anymore. Just think of me as that person who needs a little extra coaching. All right. So, in order to make the leap from describing just what happened with this group of people that I was able to ask questions to be able to make the leap from them to all the people like them that I want to be able to talk about. So inferences, that's where we're heading. We not only have to know what the summary values are for statistics. So statistics are sample specific quantities like mean, like standard deviation, like skewness. Any number that you can calculate to describe a variable is a statistic within a sample. We have to know how inconsistent that statistic would be expected to be across repeated samples. In other words, it's like, okay, I have a mean and it's 30. Like, is it 30 or is it 30? 30-ish? Right? That's what we want to know. And it turns out the more people you have in your sample, the better your ability to say 30, not 30. But we need a way of quantifying that because uptick voice is not a good way to index measurement precision. So we need to know we need to have some kind of numeric estimate as to the expected inconsistency of our mean across samples. How good of an estimate is it? How much would it wiggle around if we redid the study over and over again? That's the word I was looking for, wiggle. So we can use this information, the expected wiggle, so to speak, that's the term I'm going to go with today, to describe the range in which the mean would be expected to fall across samples, as well as to try and test whether or not the mean that we got is different from the mean that we expected it to be. So particularly for demographic variables, you may know that in the larger population, X% of the people have this characteristic. And so you go and get your sample and you hope that in your sample, you have the same roughly X% of the people so that you can say your sample is representative. Well, how close can you be or how far can you be from that specific number and still be able to say it's close enough, right? That's what we want to know. So to sort of wade into the waters of hypothesis testing, that's where we're headed. The idea of being able to answer questions using our data, questions involving just one variable at a time. So univariate hypothesis testing, all of that requires a way of indexing how inconsistent our mean is expected to be across samples. And we're starting with the mean as just the most ready example, but the same set of principles apply to any summary statistic. So if I say that my mean is 30 and my standard deviation is 5, is it 5 or is it 5-ish? Right? Same problem. It's always the case that the more people you have, the more precision you have, but we want to find a way to quantify that. So since I'm a statistician, or at least that's what some people call me, I call myself a quantitative methodologist, by the way, because my degree is in psychology, not statistics. I can make up data. So, as crazy as it sounds, a lot of the research that is done in quantitative methods involves making up fake data, fake people. It's called simulation research. And the reason that one would do this is to study the behavior of different techniques under less than optimal situations. So if you make up data, you know what the right answer is supposed to be, and you can see to what extent different ways of doing things approach that right answer or don't get the right answer, and under what conditions you need to worry about such things. So this type of process can be really useful to demonstrate certain principles that we wouldn't normally get to see in real data because all we have is just the one sample. So I made up 100,000 fake people. I have the power, all right? I made them up. Fake people are very cooperative in doing research, as it turns out. So I made up a variable with 100,000 fake people. I made up a variable that follows a normal distribution. So the picture that we had just a couple slides ago, this normal distribution has two parameters, meaning the version of it in the population that it follows that I need to know. It has a mean and it has a variance. So in this fake variable, I set the mean to be 10. I told it to make the variable such that the variance was 25. And this is a histogram that shows the distribution across my 100,000 fake people of this variable. So mean is the most likely middling value here. It is not skewed. It is symmetric. So the mean, median, and mode would be right on top of each other. And by simulating it to have a variance of 25, what I'm really saying is that even though the mean is 10, any one of these 100,000 people would be expected to be off from that mean of 10 by 5 on average. Under the normal distribution, by the way, you can expect about 95% of the cases to be within 2 standard deviations on either side. So the bulk of these data are expected to be between 0 and 20. So 2 standard deviations on either side of the mean, and that's what the plot shows here. Most of the action is within this. And I have asked for it to trace the predicted function from the normal distribution on top of these data, and you can see that it fits perfectly. So let's pretend that this is my population, okay? This is 100,000 people who all are the kind of person that I want to do research about. I don't have the money to get 100,000 people in my study though. So I'm going to take a sample, hope that my sample is representative enough to be able to make some sort of a statement about these 100,000 people that I don't have access to. Okay? You with me? So this is my population. Like, this is truth that we will never have access to, but because I made up the data, I know what it's supposed to be. All right. So what if I play God here and I create a whole bunch of samples? So I'm going to recruit subjects from my study. And let's say that I don't have a lot of money, or my subjects are hard to find, or both, or the experiment takes a long time and nobody wants to do it. All of these things can impede research. And I only get 5 people. A sample of 5 people is probably not a great sample, but it is what it is. If I got a sample of 5 people and I did that 1,000 times, so within my distribution of 100,000 fake people, I draw a sample of 5, I compute the mean. I draw another sample of 5, I compute the mean. I do that 1,000 times. This first picture up in the left-hand corner is what I get. So this picture is different. This is a level of abstraction higher than the first picture. This picture on slide 28 is a histogram that shows the variability across my 100,000 people, the population. If I take a sample out of this population, get their sample statistics, get another one, get their sample statistics, and I do that sampling 1,000 times, for 5 people per sample, can you see my mouse moving over this? Okay. For 5 people, it's the top left in this quadrant here. This is the distribution of the sample's means. So it's not people, it's means. So the first time I did this, I got a sample mean of 10.9. The second time I did this, I got a sample mean of 9.4. The third time I did this, and so on. So this is what it looks like if I only have 5 people. How well does any one sample recapture that mean of 10 that I know is true in the population? Well, fortunately, they sort of converge to the right answer, right? Most of the data, the peak of the data, the mean of the sample means is around the 10 where it's supposed to be, right? That's what this line is marking. But for any one sample, you could be way off. So out here, for instance, the x-axis stops at 15. These are samples that somehow came up with a mean of 15. A mean that's a full standard deviation of 5 higher than what it's supposed to be. Like, I just happened to sample 5 of the higher people in the distribution. Or my mean could be all the way down to 5. I just happened to sample 5 of the people, 5 people who were lower than average from the distribution. So if I only have 5 people in my sample, any one mean that I get is more like 10 as opposed to 10. Because it could be anything, right? It could be anywhere from 5 to 15 across these samples. Now, if I get a bigger sample, I double it. I get 10 people. I take 10 people, sample them, get the mean. 10 people, get the mean. 10 people, get the mean. That's this middle one right here. It's converging. It's getting closer. The samples are less spread out. They are more likely to get to the rightest answer. And if I go to 15, that tendency continues. Here's 20, here's 30, and here's 50. So the more people that you have in your sample, the less wiggle there's going to be across samples in what the mean is. The less inconsistency, the more consistent of an answer your sample mean will be. Where if you take the mean of the sample means, you should get a good idea of what the population mean is. But any one sample, you know it's going to be off to some extent. And we have to have a way of indexing how far off any one sample's mean would be from the right answer. That's what we have to know. Now I know what it is because I made up the data. So the guiding principle so far of this, the more people that you have in any one sample, the less samples are going to differ from each other and what they think the mean is supposed to be. The more people, the more likely you can say 10 and not 10. Okay, with me? So I know this is a hard conceptual leap at first because you go from thinking about your one data set and the people in it to thinking about that one data set as just one point on a distribution of possible samples. So we see this happen in politics, right? All of the different polls that you get. Each poll is a sample of people. And this poll puts this contestant 10 points ahead, and this poll puts them only 5 points ahead, and this poll puts this person 5 points behind. And you hope that across all of these polls that there's some sort of converging point at which you have a decent estimate as to what to expect in the next election. So think about one sample of data as just one poll out of all of the possible samples of polls that eventually would lead you to the population, which is the election. So the more people you have, the more consistently you would get the same answer for what the mean should be across your samples. And so here on the right-hand side are the summary statistics of these samples. So across samples, the mean closes in on 10 pretty quick. Even in samples of 5 people, the average of the sample means is pretty darn close to 10. But note what happens to the standard deviation of the sample means. So think about this. We have the standard deviation of the people, and we have the standard deviation of the sample means. Standard deviation of the people, let me go back to this picture because this is people. The standard deviation was 5. Any one person in my 100,000 people population, any one person is off from the mean of 10 by 5. That's standard deviation. If I draw repeated samples from that population, I can also look at how different the means are across those samples. And so what this rightmost column is telling me, this is something I computed using my fake data, this is how far off on average any one sample's mean is from the population mean, the mean of the sample means. So if I only have 5 people in my sample, even though on average across the samples it converges to the right answer, it converges to 10, any one sample's mean is going to be off by 2 on average. So any one sample of 5 people could have a mean of 8, could have a mean of 12, right? That gets better quick. So if I go from 5 people to 10 people, now any one sample's mean is only going to be off by 1.6. And at 15, it's 1.3, and so on. So the more people in a given sample, the better each sample's mean is with respect to capturing the population mean. It's going to be off on average to a lesser extent, more consistency, less wiggle. But that's not the only thing that matters. The other thing that matters is just how much variability the people have around the mean in the first place. So I repeated my role of playing God via simulation, and I'm comparing the distribution of 100,000 fake people here on the left that has a standard deviation of 5. So each of my fake people is off from the mean of 10 by an average of 5, versus the right side where they're only off from the mean on average by 3. So the population on the right with a standard deviation of 3 is more homogeneous. There's a new vocabulary word for you. It's a GRE word because you know what homogeneous means? Same, more similar, as opposed to relative to the more homogeneous picture on the right, the picture on the left is heterogeneous. They have more heterogeneity. They are more different. And I say this not to be amusing, but because these are real words that you will read. People will say things like homogeneous variance versus heterogeneous variance. So more alike is homogeneous, smaller standard deviation around the mean. More different from each other is more heterogeneous, bigger standard deviation around the mean. So let's see what happens now if I start from a population that has a smaller standard deviation. We see the same tendency as before, where the fewer people there are in a sample, so if I look at just 5 people, the distribution of the sample means is more spread out. Any one sample's mean is more likely to be further off from the population mean. But that tendency of being off gets better the more people that you have. So if we get to 50, then the offness is much reduced relative to what it would be at 5. And the measure of offness, so in this table here, we have the mean of the means in the first column. So all of the sample means are closing in on 10 like they're supposed to be. The question is, how good is any one sample's mean going to be as an approximation? If I only have 5 people, I'm off by 1.4 for any one sample relative to the population mean on average. But if I have 50 people, I'm only off by 0.4. And if I contrast the two populations, the top figure is a standard deviation of 3, and the bottom is a standard deviation of 5. You can see that as you get more people, the distribution gets tighter, meaning any one sample has a mean that's going to be closer to the population mean on average. But as you get more variance across people, then the further away any one sample mean is. So the more variable your people were in the first place, the harder it is to get a good estimate of the population mean. And the more people you have, the easier it is to get a good estimate. So variance and sample size are working against each other in this process. Homework question. Yeah, I'll do that periodically, by the way. I learned last semester that the YouTube stream is actually searchable. There is a closed captioning that the YouTube people put on it, and you can search through it. So you can look for things like homework question as points of review. So putting this together, the idea is we don't need to just know what the summary statistic is for a given sample, like the mean. Like my mean is 10. Is it 10 or is it 10? We need to know how precise it is. We need to know to what extent that 10 would be expected to wiggle across samples. The more wiggle, the less certain we should be in what our mean is as being a good estimate. So when we have access to the population, like I had in these pictures, I know what the right answer is. I can compute what the expected wiggle is, the standard deviation of the sample means here, how far off any one sample's mean is from the true mean. But I don't have the population in real life, right? The best you have is your one study and maybe a couple studies, but you certainly don't know what the right answer is in real data, ever. So we have to find a way to anticipate it nonetheless, even though we don't know what's true. Turns out people way smarter than me used math and figured this out already. We don't have to. We can believe. We can anticipate the wiggle of any one sample mean around a population mean with a value what's known as the standard error. So standard error of the mean is the same thing as the expected standard deviation of the sample mean across samples. It's computed using the population standard deviation divided by the square root of the sample size. So more standard deviation, more variance leads to more wiggle. That's in the numerator. And in the denominator, more people leads to less wiggle. So this gets tricky, I think, to keep straight, because when you get a set of output, for instance, you'll have a mean, you'll have a standard deviation, and you'll have a standard error. Let me say those again. We have a mean, a standard deviation, and a standard error. And the latter two sound alike, don't they? Error and deviation sound like synonyms, offnesses sort of broadly construed, but they're not. They're telling us different things at different levels of abstraction. So standard deviation pertains to one sample, like how far off is any one person in a sample from the sample's mean. If I then want to think about, okay, so I've got my sample as, now if that's just one data point in a bunch of different possible samples, how far off is that sample's mean on average from the population mean? That's standard error. And that is computed as standard deviation divided by square root of n. In practice, we rarely know what the true population standard deviation is supposed to be, so we use the sample version and call it good. That means that we're going to have to pay attention to how many people we have, though, as foreshadowing, because the more people you have, the better your estimate of the standard deviation. So let me show you that this works. So here's the same picture that we had a few slides ago. This is taken from the population of 100,000 fake people, where the true mean is 10, the true standard deviation is 5. And I went in and grabbed samples of 5 people got the mean, 10 people got the mean, 15 people got the mean, and so forth. So there's 6 conditions with respect to how many people per sample that I grabbed, and I grabbed 1,000 replications of each. So the first 2 columns we saw before. Mean of y bar across samples, that's the mean of the sample means. That's closing in on 10 in every case. That's not a problem. How far off any one sample's mean is from the population mean, this set of numbers that we looked at right here, that is what our new formula for standard error, standard deviation over square root of sample size, that is what the standard deviation of y bar, that's what it's approximating. And lo and behold, it's closing in on it pretty quick. So this formula right here, standard error, is a way to anticipate, even if you don't know what really should have happened. Given just your one sample, you can use it to anticipate what would have happened had you sampled a bunch of samples of the same sample size. So the smaller the standard error, the less wiggle you would see across samples around the population mean. The more you can say 10, the smaller the standard error.
In practice, is there like a cutoff for like what's acceptable for standard error?
There is a cutoff, but not for standard error. But standard error is going to be involved in making that decision. Okay, so how are we doing so far? It's like
So I got
45-degree thumb. Yeah, please go ahead.
will you you gave a great distinction between the two, the standard deviation, and then you explained standard error. Could you say that one more time?
I would love to.
Okay.
So it's the difference is the level of abstraction that you're talking about. So we start with people in a sample. Okay, so any one sample, you can compute the mean, you can compute the variance, take the square root of that, and get, sorry, I slipped, square root of that, and get your standard deviation. That means I need a drink. Hang on. So let me go back to the population, this picture. Okay, so this is the right answer with respect to what we're going for. Any one sample is going to have some degree of error to it because of the particular people that we pulled out of the population. So for any one sample, say of 10 people, I can get my sample mean, I can get the sample's variance, which is in a squared metric. So if I unsquare it, then we get the standard deviation, and the standard deviation is how far off any one person is from the sample mean. So person within a sample is where we're at. Standard error is not talking about people, it's talking about samples. So if I think of my one sample as just one data point, because there could be other students out there running the same sort of study and they get a different sample, right? And another student gets another sample and another university gets another sample. Each of those samples is going to have a different mean for it and a different standard deviation. The question is, how discrepant would those samples be across from one another? In those means, in those standard deviations, how much wiggle would there be across samples and how we describe each one? The standard error is the expected difference between a sample's version of a statistic and the population version. So how far off any one sample's mean is from the population mean. You can also have how far off any one sample's standard deviation is from the population standard deviation. How far off any one sample's skewness is from the population's skewness, right? You can do it for any statistic. The one that has the nice ready formula that works is standard error of the mean. And so even if you don't have the population, even if you only have one sample from it, computing its standard error is a way to approximate how different the mean would be from any one sample relative to what it's supposed to be. Okay, did that help? Okay. I'm trying to get the thumb that was at a 45-degree angle, like a little bit higher north of there. So yeah, I'm a quantitative person, right? I believe in, there's a full spectrum of okayness, where this is like meh, and this is no. And so it just, it's getting cranked up that way. Okay, so I can use my can here to demonstrate this in a different way. So quality control at the Pepsi factory, very important. My can has promised me 12 fluid ounces or 355 milliliters of calorie-free caffeine. Okay, that is what I have been promised. Any one can, though, may not have exactly 12 fluid ounces. So if I were to have some spare time with which to investigate this, let's say that I open up every can in a 12-pack, and I measure the liquid in each can. How far off any one can is inside my 12-pack from the 12 that it's supposed to be, like the mean of the sample, excuse me, that's standard deviation. Now, if I go to Costco and I start getting all the different packs, I guess it'd have to be Target or Hy-Vee that has 12 packs in this analogy, right? And I could repeat this process. The standard error would be how far off the average of any 12-pack is from the 12 that it's supposed to be. The standard deviation is how far off any one can is inside the 12-pack. Now, what would happen if I repeated my study, but instead of using a 12 pack, I used a 24 pack? Would my standard error go up or would it go down with a 24 pack? Yeah, it would go down. So standard error is imprecision, offness. The more cans in my pack, the better estimate of a sample mean that pack should give me. And if I go to Costco and I get the 36 pack, standard error should go even further down. Not that I get to go to Costco anymore. We send someone from Instacart to go to Costco for us, but some days. So cheers. All right, questions? Okay. So where was I? Standard error versus standard deviation. So standard error of the mean is something we can compute with one sample. How far off any one sample's mean is from the population mean gives us a sense of how much faith or how much confidence to have in our estimate for that one sample. So this idea, by the way, these shapes, the idea that this distribution sort of converges to something that looks like the normal distribution, the more people you have in any one sample, the closer these humps get to normal. So these are sampling distributions of the mean. In this case, this is a distribution that shows the variability across repeated samples. The more people you have, the more normal that gets. That is called the central limit theorem. Has anyone heard that phrase before? I'm guessing if you've had stats before, that's shown up. No, if not, it's okay. Because I bring it up so that you don't fall prey to a misconception that even well-meaning statisticians sometimes say. The central limit theorem does not mean that all variables become normal if you have enough people. That is not what it means. It means that the sampling distribution of a variable's mean becomes more normal if you have enough people. So it's not the people or the cans within the pack that we're talking about here. We're talking about summarizing properties of a sample as one data point and what that would look like across repeated samples. Across repeated samples, the distribution of the means of those samples becomes more normal the more people you have. And to prove it to you, I have a demonstration. I'm going to play God again and make a third fake variable of 100,000 people. Now this one has a different shape. I made this one to follow what is known as a Poisson distribution. That is French, apparently. I think it means fish or something like that. Does anyone confirm? Yes? Okay. So, as I said before, normal's not the only game in town. There's all kinds of distributions, and the Poisson distribution is commonly modeled to used to model count outcomes. So the number of things that has happened. So this distribution, for instance, was generated using a mean of 2 and a variance of 2, because in the Poisson distribution, the mean and the variance must be the same number. Because you can't have counts that are less than 0, that forces the distribution to have this sort of skewness. Take a vote. Is this positive skew or negative skew? Can take a vote. How many say positive? How many say negative? Okay, I saw some abstainers. This is indeed a positive skew because it's the way the tail goes is the way that it's named. If you want a real life example for what this distribution might reflect, let's say this is the number of times that I have to tell my son to pull up his pants, flush the potty, wash your hands before it actually happens. On a good day, only once or twice, but maybe up to 7 times. Because he really likes to tell me stories. And so he'll sit there after doing his business and he'll stand up with his pants down and keep talking about whatever it is. And I'm like, Huey, pull your pants up, flush the potty, and wash your hands, and then let's talk about this. So this is a count distribution. Others examples include put away your game and go put your shoes on. Put your game down and go put your shoes on. It's time to go to school. So maybe up to 7 times before it takes. So any one person in this sample is going to be off from the mean by an average of the square root of 2, 1.4 something, whatever that happens to be. All right. Now, does this shape right here, this Poisson, does that look normal to you? It's asymmetric. It's positively skewed. It happens to have a mean and variance that are the same number because that's what Poisson says. It's not normal, right? But nevertheless, if I take my 100,000 fake people and I do my repeated samples, I grab 5 people, get the mean, 5 people, get the mean, 5 people, get the mean. Here's what happens. Magic. The more people you have in any one sample, the more normal the distribution of that mean becomes across samples. The distribution of the mean across samples is called the sampling distribution. So with 5 people, it has some holes in it. With 10 people, it's still a little bumpy, but it's getting there. And by the time you get to 50 people, it's looking a lot like it did for the other variable that was normally distributed. So you can have variables that take on whatever sort of shapes they want to. Quantitative variables come in all forms, and that's totally fine. But even if the variable itself is not normal, the distribution of its mean across samples starts looking more normal the more people you get. And lo and behold, if I have the right answer, so to speak, the standard deviation of the means, how far off any one mean is of a sample from the population, that is really well approximated by the standard error. It works. So even though you don't know the rest of the samples or the right population, you can anticipate how different your answer would be as to what the mean is from another similar sample based on the information from your one sample, from your standard deviation, and from your sample size. All right. With me? Okay. So this standard error now is the magic button that allows us to make leaps from just our one sample to other samples and back to the population. That's the magic leap. So the first thing that we're going to learn how to do with the standard error is to form what's called a confidence interval. It is a range of uncertainty that describes across repeated samples how many of them would contain the population mean. And it requires making 2 decisions a priori to characterize your interval. Which probability distribution function you think the sample statistic follows. So we're picking normal because that's what, but we just saw that it works. And that's the only one we've talked about so far. And the other decision that you have to make is how wrong you're willing to be. How confident are you? And the most typically chosen level is 95% confident, which means 5% wrong. By the way, when you express it as how wrong you're willing to be, that 5% is going to be known as your alpha level. So we'll have this distribution here as a way to try and anticipate what happens across repeated samples, this shape of normal. But in order to try and apply it to all different kinds of data, right? The examples that I have so far had a mean of 10, a mean of 2, standard deviation of this, that. We need to find some way to make it work for all the data. So we need to standardize it. If we take our normal distribution and we convert it to a version that has a mean of 0 and a standard deviation of 1, then it's called the standard normal, and that is our new friend. So it looks like this. Probability distributions, like normal, are used to be able to express how likely any one value is that comes from that distribution. So we're going to place our results with respect to the sample mean that we got and the standard error for it that we got onto this standardized space. And so, Nikki, you asked a question like 20 minutes ago. I swear I haven't forgotten. I'm getting there. Like, is there a cutoff for what's good? Yes, but the cutoff is on this thing. The standard error helps you get to this thing. And the cutoff is your choice as to how, let me phrase it differently, at what point you're willing to say something is unexpected. Like, oh, well, that's surprising. Where's your cutoff for surprising? Where's your cutoff for that isn't likely to happen, so that looks weird to me? Well, within the standard normal distribution, we know that within one standard deviation on either side of the mean, about 64% of the observations are expected to fall. Within 2 standard deviations on either side of the mean is about 95% of the data, and within 3 standard deviations is 99% of the data-ish. And so this idea of how much percent of the time it would be expected to find something within some range is used to evaluate where your result falls with respect to expected. Like we expect some wiggle, right? Like any one sample's mean is not going to be exactly right. We expect wiggle. But how much is wiggle and how much is just wrong? Like no. So if we want to try and describe like what is the range of wiggle that we're willing to take, that we're willing to say that's within the wiggle territory. 90% of the time would give us a cut point on this distribution, and this distribution, by the way, is going to be called Z, of 1.65 on either side. So we have 5% of the time past the green on the right, and 5% of the time past the green on the left, like out. That's 10% of the area. So we would be saying, okay, anything that happens with a frequency of 10% or less, that's unacceptable. That's extreme. That is unexpected. 95% is the most typically chosen value. And that is saying that 95% of the time is within wiggle territory and 5% is extreme. But we've divided it into 2.5% on the right side and 2.5% on the left side. And if you want to be really, really certain, like you are unwilling to flag something as being unexpected, like you want to be really conservative, then 99% would give you a 0.5% of the time on the right and a 0.5% of the time on the left. So these are cut points that we will use to create intervals around our sample statistic that describes the expected range across samples, known as a confidence interval. So I took statistics as an undergraduate, and back in the day we had statistics textbooks that had these big ass tables in the back. Do you remember these? Any of you who've been through this? They had like a Z table and an F table and a T table and a Q table and whatever, right? And upon a time you had to like look in the table and be like, okay, my number is here and my other number is here, and that means my answer is this tiny little square. We're not doing that. You know why? Because people who've programmed this shit into Stata and SAS and R and other places, they put the tables in there. So the days of having to use analog devices to figure out like what your answer should be relative to some distribution, we're not doing any of that. That's what software is for. So if you remember Z tables in the back of some book, that's what I'm talking about. But modern software allows you to directly say for any one value of Z what the p-value is that goes with it. This is a term we haven't gotten to yet, but p-value is the probability of observing a result that is more extreme than that point. So what purple means here, the 2.58, is that we would expect to find a result more extreme than 2.58 this way or that way less than 1% of the time. And you can get exactly how much less than 1% is. 5% is the conventional level, that's the middle one. And so any result that happens less than 5% of the time would be flagged as unexpected. out of the range of expected wiggle due to sampling error. So that will be our first task next time, is to start exploring confidence intervals around our sample mean. All right, how we doing? Okay, so take home points from today. Any one sample is going to give you a number that summarizes its central tendency, like the mean, like the median. A number that summarizes its dispersion, like the standard deviation, how far off any one person is from the sample mean. But in addition to those numbers, if we want to be able to talk about anything other than the individuals in our sample, if we want to extrapolate back up to the population we care about, we have to have some way of indexing the consistency of those numbers, how believable they are. And the way that we're going to do that is to get standard errors. Standard error conveys how far off on average that sample statistic would be from the population version. How much wiggle is there if you were to repeat your study and not get the same results each time? How different would they be? And we're going to use that information to create intervals to describe the range of expected wiggle, as well as to make cut and dry decisions as to whether or not a given result is too weird to have happened by chance. That's your cutoff value we're heading to. Okay. All right, so it is Thursday. It's not garbage day, which means it's Thursday. This is my new pandemic schedule where every day is the same pretty much. But if it's not garbage day, then that means it's Thursday, which means I say, have a good weekend. Please take care of yourselves and let me know if I can help you with anything. All right. Okay, peace out, guys. Thanks for coming.
Thank you.
Thanks. Bye-bye.
Bye-bye.